In today's lecture, we are going to discuss about the introduction to machine, and then classifications of machines, and followed by DC generator, its construction and working principle, and finally we are going to discuss about the types of DC generator. Machine. A machine may contain several parts for doing a specific work, whereas an electrical machine is a device that converts mechanical energy into electrical energy or electrical energy into mechanical energy. The electrical machines are classified into two types. One is static machine and another one is rotating machine. Static machine means it doesn't have any rotating parts, whereas rotating machine may have a rotating part. For example, they have stator and rotor. A rotor is a rotating part in the rotating machinery. Okay, the static machine is further classified into transformer, okay, which doesn't have any rotating parts. It is further classified into step-up transformer, step-down transformer, auto transformer, like that. Whereas rotating machine is further classified into DC machines and AC machines based on the principle of operation. Okay, and DC machines are further classified into DC generator and a DC motor, whereas AC machines are further classified into synchronous machine and asynchronous machine. Synchronous machine means it runs at a rated speed, whereas asynchronous machine which doesn't runs at a rated speed. Okay, then further synchronous machine is classified into synchronous generator and synchronous motor, and asynchronous machine is further classified into induction machines, right? Now let's discuss about DC generator. An electrical generator is a machine which converts mechanical energy into electrical energy, and it is same. If it is a DC generator, then it converts mechanical energy into DC electrical energy, right? So this energy conversion in DC generator is based on the principle of production of dynamically induced EMF. Okay, that is according to Faraday's law of electromagnetic induction. It states that whenever a conductor cuts a magnetic flux, a dynamically induced EMF is produced. Based on that principle, this DC generator operates. Okay, and this EMF produces a current to flow if the circuit is closed. Right. This is an animation showing the working principle. So according to Faraday's law, when a conductor cuts the magnetic flux, an EMF is induced. So here it is a conductor. This is a conductor. Okay, it's a copper coil, and this is a magnet. Okay, so the magnet produces magnetic lines of force, and this is a conductor. When the conductor cuts the magnetic lines of force, you can see an EMF is induced, right? So that is the basic concept. And here you can see the magnetic field is produced by North Pole and South Pole. Okay, there is a magnetic lines of force you can notice, and this is a conductor, and it is a single loop conductor. There is only one loop. This is for understanding. Okay, whereas in practical there will be many coils, but here in order to have a better understanding, there is only one coil. Okay, and this coil is connected to the split rings. Okay, here you can see there are two split rings, and the white color one is the brush. Okay, and it is connected to the external circuit, and here you can notice whenever the conductor cuts the magnetic lines of force, an EMF is induced in the circuit, and it is unidirectional. Why? Because of this split rings. Okay, the split ring converts the bidirectional current which is generated in the armature conductor to the unidirectional current to the external circuit, right? And here you can notice how the single loop generator produces an unidirectional current from 0 degree at 120, 180 degree it reaches the maximum, and again at 180 degree it reaches 0, and 270 degree it reaches maximum, and then at 360 degree it reaches 0. So the cycle repeats, and since the waveform is unidirectional, we are saying it is a DC generator. Okay, now let's discuss about the construction of DC generator. These are the pictures of DC generator, and this is a simplified picture. And here we can notice the parts of the generator. Okay, so the first one is the yoke. So this is the outer covering of the DC generator, which gives mechanical strength. Okay, basically for providing a good mechanical strength. Okay, and then you can see the poles. Okay, you see the pole, north pole, south pole, north pole, south pole. There are four poles in this DC generator. Okay, and these poles, it gives support for the field winding. You can see in the pole there is a field winding. Okay, there is a field winding which is wound on this pole, and this pole is having a pole shoe for giving better flux. Okay, for providing better flux, right? And these are the stationary parts like a yoke, then pole shoe, field winding. They forms stationary parts of the generator. And next we can notice the armature. Okay, that is at the inner circle, and this armature is having some slots. Here you can note the slots, and in these slots there is a small circle, and that is nothing but a conductor. Okay, so in order to produce an electromotive force, we need a magnetic field and a conductor. So the magnetic field is produced by this north pole and south pole, whereas we need a conductor to cut the magnetic flux. So those conductors are there in the armature, so they are called as armature conductors. So these two parts are most important for generating an EMF, right? And this armature is also having a commutator. Okay, all the winding will be connected to the commutator. For what purpose? To convert this alternating current generated in the armature conductors to the unidirectional current for the external circuit. Okay, and then later it is connected to the brush. Okay, and from the brush it will be given to external circuit. So this is the simple construction of DC generator. So again, these are the parts of the DC generator as we have discussed. It consists of yoke or magnetic frame, and then pole core and pole shoes, and then field coils or pole coils, and then armature core, armature winding or conductors, and then commutator, and finally brushes and bearings. So it is the outer frame of the DC machine which provides mechanical support for the poles, and it carries the magnetic flux produced by the poles. Pole cores and pole shoes. Pole cores are joined to the yoke with the help of bolt or welding. Okay, and these pole cores are laminated to each other. And the main purpose of the pole core is to support field coils, right? And they spread out flux in the air gap uniformly. So this spread out is due to the pole shoes. Pole coils or field windings, they are usually made up of copper because it acts as an electromagnet. So for electrical conductivity, copper is used, and since it is a better conductor. And these field coils are former wound and placed in each pole and are connected in series. So everything is connected in series, and it is placed in each and every pole. Okay, so that it can act as north pole as well as south pole, and they are wound in such a way that when energized they form alternate north pole and south pole. That is what we discussed. And when current is passed through these coils, they electromagnetize and produce corresponding poles for necessary flux. Okay, so that the armature conductor cuts this flux when the armature conductors are rotating. Right. This armature core is going to act as a rotor of the DC machine, whereas the field coils act as the stator of the DC machine. Okay, and this armature core is fixed to the shaft. Okay, there is a central rod called as shaft, and that shaft is basis for this rotating operation, right? And this armature core is cylindrical in shape with slots that carry the armature conductors. Okay, and the armature is built up of thin laminated circular steel disc. Okay, this is also laminated with respect to each other in order to reduce these eddy current losses. Right, armature windings. Okay, they are basically the conductors. Okay, they are basically the conductors which is placed in the armature slots, and these conductors are lined with tough insulating material so that it won't get short circuited. Commutator. Yeah, the commutator is also made up of copper segments insulated from each other, and the main function of the commutator is to collect the current generated in the armature conductors, which is alternating in nature, and then it converts or it converts that alternating current induced in the armature conductor to the unidirectional current. So this also act as a rectifier. Okay, since the AC is converted to DC, it can also performs this rectifying action. Okay, and brushes. These brushes are usually made up of carbon or graphite. Okay, and they actually rest on the commutator and slide on the commutator segments to collect that converted unidirectional current to the external circuitry. Okay. Types of DC generator. The DC generators are classified into two types according to the way of excitation of the field. Field means magnetic field. We need magnetic field. So here we need to excite the field coils to produce magnetic field. So according to the way of the excitation, it is classified into separately excited and self-excited. So here in this diagram, you can see that this is the field winding and this is the armature winding. So this field winding and armature winding are important to generate an EMF. Okay, right. So here in separately excited DC generator, you can see that the field winding is connected to an external supply. Okay, and due to this external supply, this field winding got excited or energized and it produces the magnetic field or magnetic flux, so that the armature conductor cuts the flux and it generates or produces current in the external circuit. Okay, so in separately excited DC generator, the field winding is excited with an independent supply. Whereas in self-excited DC generator, there won't be any separate supply for energizing the field coil. So it uses an internally generated EMF for energizing the field coil. So that we call it as a residual magnetism. So here it uses the residual magnetism to energize the field coil. That is the difference. And this is further classified into series wound, shunt wound, and compound wound DC generator. Right. Say series wound self-excited DC generator. So here you can notice, first you can notice that there is no separate supply for energizing the energizing the field winding. Okay. So this field winding is energized due to residual magnetism. Therefore, it is called as self-excited. And next one, it is called series wound because this field winding and the armature winding are connected in series. That is why it is called a series wound DC generator. Okay. The next one is shunt wound DC generator. So here you can notice in the diagram that the field winding is connected in parallel with the armature winding. So that is why it is called a shunt. Shunt means it's connected in parallel. Okay, the field winding is connected in parallel with the armature winding, and you can notice that there is no separate supply for exciting the field winding, and therefore it is self-excited. In compound wound self-excited DC generator, you can notice that part of the field winding is connected in parallel to the armature and part of the field winding is connected in series to the armature. So it is a combination of both shunt and series wound DC generator. Okay, and when series field aids the shunt field, then the generator is called as commutatively compounded, and if the series field opposes the shunt field, then it is said to be differentially compounded. This diagram gives you the overall classification of DC generator. Okay, so as we have discussed, it is broadly classified into self-excited and separately excited based on the excitation of the field winding. So here you can notice there is a separate supply given to the field winding, and in self-excited you can see that there is no separate excitation for this winding. Okay, and then self-excited is further classified into series, shunt, and compound, and compound is further classified into long shunt and short shunt, right? So this is the uh, diagram showing all the types of DC generator. Thank you.